this video we'll prepare malonic acid. Before we start though, a word of warning. This reaction uses inorganic cyanide salts and also chloroacetic acid. Two potent metabolic poisons in one reaction. So please don't attempt this unless you are trained and confident. We're starting with a crude sodium-potassium cyanide salt that we prepared using the method in a previous video. This is 14 grams of the reaction product, which contains 10 to 11 grams of mixed sodium-potassium cyanide salt. First we need to separate the cyanide from the iron byproduct of the reaction, so we measured out 25 ml of water. We've put the crude cyanide in a beaker, and we add the water to dissolve the inorganic salts. This takes quite a bit of stirring, and heating the mixture slightly helps as the cyanide will cool the solution as it dissolves. Just lumps of iron left now. We could filter this solution, but instead we'll decant of the supernatant liquid because we want to minimize exposure to this highly toxic substance. Here we go. This is our cyanide solution and we'll use this later on. Now for our other key ingredient. This is chloroacetic acid. We may do a future video on making this, but for this experiment we're using a commercial product. This is 15 grams, which is just slightly less than the molar equivalent of cyanide we're using in the reaction. Take care with this. For once the safety labeling is understating the toxicity of this compound. Despite the tame warning, this is a nasty poison and you need to be careful to avoid skin contact. We measured out 30 ml of water, and then added this to the chloroacetic acid crystals. It takes quite a lot of stirring to dissolve, so be patient. Here we go. Now the first thing we need to do is convert this into a solution of the sodium salt. So measure out 6.4 grams of sodium hydroxide. This is approximately equimolar. Chill down the chloroacetic acid solution, and then slowly add the sodium hydroxide to it with stirring, a bit at a time. The neutralization produces quite a bit of heat, so take time over this and allow the mixture to cool as needed. This took about 20 minutes, and here's our solution. Now we need to test this with indicator paper and make sure it is at pH 7, i.e. neutral, before we proceed. Looks like we overshot. No problem. We'll add some dilute hydrochloric acid and test again. If we overshoot the other way, we'll add sodium hydroxide solution and keep going until we're at pH 7. Great. This is now neutral. It's really important to get this right. If the solution is even slightly acid, then when we add cyanide and deadly hydrogen cyanide gas will be produced. We do not want this. So now back to our cyanide solution. We need to heat this so that it's at around 40 degrees C. The reaction is sluggish at room temperature, but will get started better above 40 degrees. And now for our neutralized sodium chloroacetate solution. Again, warm to 40 degrees. Time for the reaction. We add the cyanide solution to the sodium chloroacetate. We've put a thermometer in the mixture so you can see what's happening. Slowly at first, you can see the temperature start to rise as the reaction starts off. Give the mixture a good swirl, and the temperature will continue to rise. With the small volumes of reagents we've used, this won't go too high, but on scaling up you need to be very careful. If the temperature rises above 80 degrees C, then side reactions will occur and deadly cyanide gas can be released. We're pretty cautious and we prefer to keep things below 60 degrees. So around now you want to cool the beaker using some cold water, Don't cool too much, just back down to around 40. The temperature then rises again, and soon plateaus. This is as high as we got. About 30 minutes in, we can now start to gently heat the reaction mixture on a hot plate. After 30 minutes at a temperature of nearly 80 degrees, the first stage of the reaction is complete. We now need to hydrolyze the intermediate cyanoacetate compound. To do this, we will use the further 7 grams of sodium hydroxide. We're using 20 ml of cold water to dissolve this. The solution is hot, so allow to cool. And now add to the reaction mixture. You can see there are some particles in our reaction mixture. This is just residual iron left over from when we decanted the original cyanide solution. Now we've added the sodium hydroxide. The nitro compound is going to hydrolyze and ammonia gas will be created under the alkaline conditions. You can see the change in the indicator paper. Now heat the solution on the hot plate until it reaches the temperature of 100 degrees C. Just before that point you'll get lots of bubbling and ammonia gas produced. Now we need to keep the mixture at 100 degrees C for the next 3 hours to ensure the reaction completes. As evaporation occurs, white solids will form. As this happens, just add a little water to redissolve them again and keep going. Here's our mixture after 3 hours of heating. There's tiny hint of ammonia remaining, but that's all. Now allow to cool down, and then chill the mixture. Now we're going to acidify the mixture in order to convert the sodium salt of our product into malonic acid. We'll use concentrated hydrochloric acid to do this. Add the acid slowly to the mixture. The HCl gas and residual ammonia create a nice white smoke of ammonium chloride. Note that the sodium hydroxide and heat will have also destroyed any excess alkali cyanide as well, so there should be no HCN gas produced. After a while we're getting a little effervescence, which is probably CO2 due to the absorption of some atmospheric CO2 by the alkali. Let's now check the pH. It's just very slightly acidic, and as you add the hydrochloric acid you will notice that the pH doesn't change for a long time due to a buffering effect of the solution. So we continue adding the acid in order to convert all the sodium malonate into malonic acid. Once it's all converted we'll see a large decrease in pH due to there being free hydrochloric acid in solution. Slightly more acid now, but not significantly. Overall we've used around 25 ml of concentrated hydrochloric acid before we saw the pH decrease right down, indicating a strongly acidic solution. At this point we got a fine white precipitate appearing, as you can see. Now that's strongly acid. So we're done. We now need to evaporate down, so we placed into a larger beaker to provide a larger surface area. We heated this to 100 degrees C again and allowed it to slowly evaporate down into a paste. Be careful with the heating because malonic acid will decompose with too much heat into acetic acid. If you smell vinegar, then you are heating too strongly. Soon a crust appears on the liquid and it reduces down into a thick consistency. We also added a stir bar to help distribute the heat and stop local overheating occurring. Once we had a paste, we transferred the mixture into a Pyrex oven dish. And then we baked it in the oven at 100 degrees C for 3 hours to dry it completely. We occasionally broke up the solids using a spatula so that a powder was eventually formed. The normal procedure, which we know works, is to extract this using ether. but we wanted to do an experiment and see if it was possible using ethanol instead. So we measured out 25 mL to begin with of absolute ethanol and added this to the mixture, mixing and breaking it up very thoroughly. We also gave it a quick blast in the microwave to heat and help extract. Then we filtered off the ethanolic filtrate using a vacuum pump. Here's the filtrate. Looking good so far. In theory, ethanol should dissolve malonic acid fairly well. And on cooling this filtrate, we're getting crystals forming in the solution. So we repeated the ethanol extraction and got another 20 mL or so of filtrate. Then we combined these in a flask and used a vacuum and hot water bath to evaporate off the ethanol. But a problem struck. We didn't get crystals. Instead we could only get a syrupy slightly yellow liquid, as you can see. Even on chilling down, this didn't yield any crystals. What has happened is that the heat together with the ethanol and the acid have formed an ester, diethylmalonate. Any remaining malonic acid looks to have dissolved in the ester. It does have a nice fruity aroma though. We didn't think this would happen because it normally takes an acid catalyst to make this work. But it's a good lesson. Here's the solids that we retained from the ethanol extraction. Let's use the traditional method and see if we can get any malonic acid out. So we measured out 50 mL of diethyl ether and added this to the solids in a beaker. We then spent a good 30 minutes stirring and breaking up the solids to try to extract as well as possible. Then filtered again. And we've got a nice clean looking filtrate. We'll evaporate this off under vacuum on a water bath. And we've got a tiny bit of white solid. It's a bit damp, but it's a nice color. The result was a bit disappointing. About half a gram of damp white crystals. The good news is that the ethanol extract seemed to remove impurities, so it's very clean. But despite our efforts to keep the ether and the glassware very dry, it's still damp and it seems very difficult to obtain the dry product without heating it up and risking decomposition. So we've learned that this is a pretty easy reaction to carry out on a small scale, but the workup is lengthy and you have to use either diethyl ether or tetrahydrofuran as an extraction solvent. It also helps to do a lengthy extraction on the solids in order to get all the malonic acid out. This might be enough to do a clock reaction on a miniature scale, but we'll see. Thanks for watching and stay tuned for more reactions.